talking about 17.2, which is Stokes' theorem. Stokes' theorem is very, very similar to Green's theorem, only we're generalizing. Green's theorem was only in R2. Stokes' theorem is going to talk about surfaces that are up in R3. But we'll see some of those similarities. Our goals for today are to be able to compute the curl of a vector field in R3. We've talked about scalar curl before, and now we're going to talk about curl for three-dimensional vector fields. We're also going to define the boundary and the orientation of a surface, and then we're going to state and apply Stokes' theorem. That's the big topic, and we'll go through a couple of examples of Stokes' theorem. And our geometric interpretation of Stokes' theorem is going to be here, where we describe surface independence for curl vector fields. We have some interesting results of what happens, what is the relationship between the boundary of a surface and the vector surface integral over the curl of the vector field function. So to start off, we're going to look at what the curl of a vector field in R3 looks like. So let's let F be our vector field. Notice that I have points in R3 as my inputs. I have x, y, and z as my inputs. And I have three component functions as my outputs. So my outputs in this case are vectors in R3. And our curl, this is my definition, and there are a couple of ways that I can notate this, that we say that the curl of F, curl of F is equal to our gradient operator crossed with our vector field function F. This looks a little funny because typically when we think about our gradient, we think of it as an operation that we do on something. We don't think of it as a gradient operator. So let me explain a little bit more about what I mean by this. Here, we're thinking of our gradient operator as a vector given by partial derivatives. So the first component of this is my partial derivative with respect to x. My second component is my partial derivative with respect to y. And the third component is the partial derivative with respect to z. So what does that mean if I take the cross product of this gradient operator with my three-dimensional vector field? Well, recall that cross products are given by the determinant of a matrix. So I'm going to compute the determinant of the matrix where I have I, j, and k in my first row. My second row is going to be this gradient operator, my partial derivative with respect to x, my partial derivative with respect to y, and my partial derivative with respect to z. Notice that there's nothing filled in here. That's going to come from these final pieces. My final row is going to be what I'm crossing this gradient operator with, and in this case, I'm crossing it with my f function. So the first component of the f function is f1, the second component of the f function is f2, and the third component of the f function is f3. So now that I've set up this matrix, and this is always going to be the case, this is how we define our curl. Now I can just plug and chug and find the determinant of this. So what does it take to define the determinant? I take I times the determinant of this minor 2 by 2 matrix. And what does that look like? I'm taking I times my partial derivative with respect to y times f3, and that becomes my partial derivative of f3 with respect to y. So what just happened there? I'm looking at this times this, and I'm notating that as the partial derivative of f3 with respect to y. Minus this diagonal, which in this case is the partial derivative of f2 with respect to z. And that's my ith component of this cross product. This times this, maybe I'll even get it in green. This times this minus this times this. So let's move on to our jth component. So our jth component is going to be given by the negative of j times this minus this times this. So in this case, it's going to be my partial derivative of f3 with respect to x minus my partial derivative of f1 with respect to z. And I'm running out of room, so I'm going to skip on over to the next line. My final component of this determinant is going to be my kth component. And in this case, my kth component is the partial derivative of f2 with respect to x minus my partial derivative of f1 with respect to y. So this is a long and messy formula, and if you wanted to, you could memorize this formula, because this formula is my curl of f. And I think I'm going to write it out one more time really clearly in vector notation. My first component is my ith component, and it's df3 dy minus df2 dz. And then I'm going to distribute this -1. You need not, but I'm thinking of my second component function. When I distribute the negative sign, I end up with the partial derivative of f1 with respect to z minus the partial derivative of f3 with respect to x. And then my final component here is going to be my partial derivative of f2 with respect to x minus my partial derivative of f1 with respect to y. So that's my vector notation for the curl of f. And that's something that I'm going to highlight here. So unlike what we got with scalar curl, where our scalar output was a real value, in this case, this output, the curl of f, and sometimes I might write it like this, it's the function f, is a vector in R3. That's important to know, that when you do this cross product, you don't come up with a single real valued number. You need to make sure that you come up with a vector of 3 components. So let's do an example. And let's let our f of x, y, z be equal to, I have this written out, I don't think it really matters, xz y squared plus x and e to the z. So now I want to compute the curl of f, which I'm going to notate as the gradient crossed with f, which is going to be the determinant of the matrix given by I, j, k. And in my first column, I use my gradient operator, and it's each of my partials with respect to each of the variables. The partial with respect to x, the partial with respect to y, and the partial with respect to z. And then my final row is going to be each of the components of my f function. So in this case, I have xc as my first component function, I have y squared plus x as my second component function, and I have e to the z as my third component function. So let's take the determinant of this matrix. Again, when I look at the ith component, it's the determinant of this minor 2 by 2 matrix. So I'm taking the partial derivative of e to the z with respect to y, and then I subtract the partial derivative of y squared plus x with respect to z, and then I subtract the j component term is going to be the partial derivative of e to the z with respect to x, and then I subtract the partial derivative of xc with respect to z. These are all function inputs. Maybe the parentheses make that a little more clear. And then finally, my kth component is going to be the partial derivative of y squared plus x with respect to x. And then I subtract out the partial derivative of xz with respect to y. So let's go ahead and compute this. That means that in my ith component, if I were to represent this as a vector, I see that my partial derivative of e to the z with respect to y is just 0, because both these components are 0, right? There are no y's in here, this is just a constant. Similarly, this term is also 0. There are no z's in this formula. So my first component is 0. My partial derivative of e to the z with respect to x is also 0. Haha, but look, here this one isn't. The partial derivative of xc with respect to z, we treat x as a constant, and that's going to be the partial derivative. So I'm subtracting a negative x, and I end up with positive x. And then finally, I see that my partial derivative of x, or y squared plus x with respect to x is 1. And then I subtract out my partial derivative of xc with respect to y, which is just 0. And we're done. So this is representing the curl of our f function. So hopefully, at this point, you might be asking yourself, what's the relationship between the curl of a 3-dimensional vector field and a 2-dimensional vector field? Because we talked about the scalar curl of 2-dimensional vector fields. And so I'm going to, let's consider what happens if I have just a 2-dimensional vector field. So this is what we saw last time with Green's theorem. I have a 2-dimensional vector field, my inputs are just x's and y's, and my outputs in this case are p's and q's. And it gives me, let's pretend that instead of being a 2-dimensional vector field, that it is a 3-dimensional vector field. Only in this case, our third component of it is 0. And that's something that's not that unrealistic. We're saying that we're only considering what's going down in the xy plane, and so our z components of each of these vectors would just be set equal to 0. It turns out, and I'll highlight this with a different color, my scalar, we're calling this our scalar curl of f, is exactly the same thing. I can use the same formula. The only difference is, this was from the specific example before, we don't like these things, is that because this is a function of just x and y, my z's are just 0. And my first component function and my second component function, I could still call p and q, because that's going to align with our scalar curl notation that we saw before. And our third component is just equal to 0. So let's see what happens when we take this determinant. When I look at the ith component, I get my partial derivative with respect to y of 0 minus q times 0, which is just going to be 0. I subtract out my jth component, which is my partial derivative with respect to x times 0 minus 0, plus my kth component, and in this case, k is going to be my partial derivative of q with respect to x minus my partial derivative of p with respect to y. And notice this is exactly what we should expect. That last time when we were talking about scalar curl, we defined scalar curl to be exactly the partial derivative of q with respect to x minus the partial derivative of p with respect to y. So it's exactly this kth component. So we're essentially taking the magnitude of what this 3-dimensional vector is. So if we think of this as a 3-dimensional vector, curl always gives out a 3-component vector, whereas scalar curl is just going to look at that third component, which is our dp, or dq dx minus dp dy.